Then initially you have low frequency, but that changed to high frequency because this edge shifts a bit. Let's see what happens when you do the actual experiment. This is the experimental result. The low intensity result is here. That's the gray curve showing transmission versus detuning is a funny kind of frequency, right? It's 1 is at the edge and 0 it's at the break frequency. So here you are at the edge, and for this at low intensities, the transmission is low here and it is high there, exactly as you might expect. It doesn't go down to 0, it doesn't go up to 1 here for experimental reasons. Don't worry about that. Now you increase the intensity, and you might expect naively this thing to shift that way, as we discussed earlier. But what happens instead? That you get these step-like features, right? 1, 2, 3 steps. And so this is an example where your expectation is really not met. It's really quite considerably more complicated than this mere shift of the refractive index. Of the band gap. And what I want to do in this presentation is explain to you what is happening here and the rich physics that is associated with this step-like behavior that you can see. All right, so that brings me then to my outline. Given the pedigree of most of you, I have just one slide on slow light. I just want to talk about nonlinear slow light and turbo gap solitons, which is the key, or one of the keys to the result I showed on my previous slide. I'll just show you the high intensity results, where to go next, and then a couple of slides on the optics express stuff. Okay, just the one slide I have on, one slide I have on the motivation for slow light and why we're interested in, and I think many of you are interested in it for the same reason. That all comes out of the relation here, where S is the energy flow, U is the energy density, and Vg is the group velocity. So if the group velocity is very low, then for a fixed energy flow, your field density, and therefore your fields themselves are very strong. There's no deep mystery there as far as I'm concerned. What happens in these geometries, like the fiber gratings and the photonic crystals, is that the light kind of propagates through, gets reflected, comes back, is reflected again, and goes ahead. And so it doesn't go through this medium in one hit. It gets reflected many times along the way, and therefore it pops out on the other end later than you might expect. And that's how I see the low group velocity there. Therefore the light spends more time in the medium, and therefore it's perhaps not surprising that associated fields are higher. Okay? So that's basically what the physics here is. Now it turns out that nonlinear optical effects are not sensitive to S, they're sensitive to the energy density U. And so if you have slow light, then if you somehow manage to keep your energy flow the same, which is a different story I'm not going to get into here, you find that your energy density goes up, and therefore your nonlinear optical effects go up. And that is the reason we're interested in that, and many others as well. These are some of the key early references in this area. This shows that slow light leads to a lowering of the modulation drive voltage. This paper by Beck and all here, yes, I would like to meet you afterwards, showing lowering of the switching threshold, and then some of the work that we did, or my colleagues, I was not involved in this, is showing that with slow light you can get third harmonic generation again because of these enhanced nonlinear effects. Now, you don't get things for free. There are some fundamental limitations to this, and David Miller from Stanford published one fundamental limitation a couple of years ago, which can be written in this way. Delta T is the maximum delay you can get. Delta F is the bandwidth of your signal, and those two are limited, or have to be smaller than this, which is the length, the index contrast, and the refractive, and the wavelength. And so yes, I guess the longer the structure, the more delay you can get. But let us look at this in a slightly different way. Delta F for a transform limited pulse, the bandwidth is roughly the inverse of the pulse length. So, and the factor there is avoided unity. So what you see on the left-hand side is essentially the delay you get divided by the pulse wave. And I call that the fractional delay. And the fractional delay is limited in some way. You can make the structure longer and you get more delay, but there is a natural limit to what you can do. Now, when you run into these fundamental limitations, it's always useful to look at the assumptions made. I consider these assumptions to be like the fine print in a contract, right? It's the way to get out of things if things go wrong. And so what assumptions did David Miller make in his work? He assumed, for example, that the process is linear. And so if you have a nonlinear process, presumably this no longer applies and you can get out of it. It's an escape clause in your contract. There are other limitations, the effect of losses of curves, and my colleague Rob Tucker from Melbourne has written some key papers there. There's an effect of dispersion, which I will be talking about in particular. It's pointless to delay something if the thing is ripped apart by dispersion along the way, right? So you have to do very careful dispersion measurements, and this is, management, and this is the reason this dispersion that some of the early work, the delays were, these fractional delays were rather limited. Okay, let me then tell just about some of the geometries. This is the schematic of this fiber grating geometry I described earlier, and this is a schematic, no, sorry, this is an electron micrograph of a photonic crystal, and it's a type of standard geometry that people use to do these slow light measurements. I guess the one thing I put out to you are the rough numbers, the delta N here is 10 to the minus 3, of course, but they're very long. Resonant photonic crystals are typically much shorter, but the refractive index contrast is avoided unity. Okay, now there have been many papers on sculpting of dispersion relation to get this low group velocity. Krauss, in collaboration with some of you guys, have done this. I decided to include a paper by Baba et al. From Japan, who, like some of you, have made this dispersion relation with these very flat regions where the omega decay, the group velocity is very low. He managed to broaden it by chirping the structure, and you can see here, the details don't really matter, that he can delay things by 20 picoseconds or something like that. Okay? I just don't want to get into this more because I have my own plan to follow. This is again this fiber grating geometry that I was talking about earlier. This is now the Bragg condition that I had earlier, but in terms of wavelength rather than frequency. So this is then, so what this, for this very weak refractive index contrast, what happens to your band structure? Your dispersion relation is quite simple. Here you have the dispersion relation, which is the lowest order straight line for a uniform medium, and then we have this very weak modulation in the refractive index. You get a little gap